In this next program, we have declared a one-dimensional array. The array name is num, and from our previous lecture material, we discussed that when you include an initializer, you don't have to specify the size of the array. So you can leave this empty. And how will the compiler know the actual size of the array? In this case, that you did not explicitly indicate the size of the array. The compiler will know the actual size of the array by simply counting the number of elements you listed here in the initializer. So since there are 1, 2, 3, 4, 5 elements or 5 values in the initializer, then the compiler will allocate 5 integer type memory locations also for the one-dimensional array num. So say if this is the RAM or the main memory representation, and these are the values. So remember that by default, the index of the array starts with 0. So the first element, which is this one, 6, is your num0. The second is your num1. The third is num2. The fourth is 8, and that is num3. And the last one, 2, is your num4. So again, by default, the index of the array starts with 0. So if the size is 5, like in this case, there are 5 elements, then the indices would be from 0 up to 4. So if you denote the index to be I, then the value of I would range from 0 to 4. 5 is not included since we start with 0. So these are 5 elements, num0, 1, 2, 3, and 4. And each location is 2 bytes. Why 2 bytes? Because the type of each element is integer, and you know for a fact that integer type values are allocated 2 bytes of memory. So each of this location is 2 bytes since each one is type integer. So what does this for loop displayed on the screen, and why are we using a for loop? We use a for loop to access the elements of the 1D array because it is the easiest way to access or to traverse the one-dimensional array. You could just say, like in this case, we use a local variable I as our for loop control variable, and we initialize it to 0 because the index of the first element of the array is 0, and then this is less than 5, which means that your I is only until 4. Okay, and then this is how we update the value of I. We increment I so that from num0 we would go to num1, and then after num1 we would go to num2, and so on. And then we have here a new line. That is why, as you can see in the output, each value occupies one line. Now, this is the easiest way to access array elements using the notation num, which is the array name, and then followed by the square brackets. And inside the square brackets, you're going to specify the index of the element you want to access. So it would be num I, okay? This one here. So on the first iteration of the for loop, when I is equal to 0, you would display num0, and then you increment it, your I becomes 1, and the next time you execute this loop body, that's the second iteration, this would now display num1, and then the next iteration num2, next iteration num3, and so on. Okay, so this is on the first iteration, second, third, fourth, and fifth iteration. In this fourth example, we declare the same 1D array and same value 61382, but this time we are using a single indirection pointer p. So as you can see here, we declare p with a prefix asterisk, so that makes p a single indirection pointer. while I here is an ordinary variable, integer variable. And what we do here is, just like the program earlier, is to access the array elements from the first element up to the last element using a for loop, but this time we are going to use a pointer. This is another way of accessing array elements. The previous one, we use a for loop control variable I, the syntax which is num I. This is the commonly used way of accessing array elements. You specify the array name, like this one here, num, and then you use square brackets and you specify here the index of the element you want to access. So again, this is the default way or the commonly used way of accessing array elements. The second one is, as demonstrated in this example, it is using a single indirection pointer. And how do we do that? So say this is the RAM or the memory representation, and these are the elements of the array stored inside the RAM. The first element is 6, and that is referenced as num0. And the second is 1, referenced as num1. And the third is 3, which is referenced as num2. And the fourth is 8, referenced as num3. And lastly, 2, referenced as num4. So the whole structure here, from num0 to num4, that is the total allocation of array num. And so since there are 5 elements, first, second, third, fourth, and fifth, 5 elements, times each element is allocated 2 bytes, since the data type of each element is integer, and integer, recall that it is allocated 2 bytes of memory space, and so each element which is type integer is allocated 2 bytes. So there are 5 elements times 2 bytes. The total memory allocation for the whole array is 10 bytes. 5 elements times 2 bytes each element. So the total memory allocation for the array num is 10 bytes. And take note that by default, the array name num is a single indirection pointer to the first element, which is num0. So it's like we have here a single indirection pointer with the name num pointing on the first element. So since num, the array name, is a pointer to the first element, that means that the actual value of num is equal to the memory address of num0. That is why we say here num is equal to ampersand num0. Okay, so every time you declare an array in your program, the compiler will automatically create a single indirection pointer with the name same as the array name, and the value of that is the memory address of the first element. That's why we have here a pointer pointing to num0. And since in our for loop in here, we initialize p to be equal to num, where p is a single indirection pointer. So whatever is the value of num, which in this case is ampersand or the memory address of num0, that becomes also the value of p. And therefore, p is also pointing on the first element. So we have here p pointing on the first element. So now p and num are both pointing on the same memory location, which is the first element of the array. So num is equal to the memory address of num0. Say for example, the memory address of num0 is 81. So this is 82, this is 83, 84, and then this is 85. So if num is 81, the memory address of num0, and then you assign num to p, therefore p is also memory address 81. So it is like both P and num are pointing on the first element num0. So we have here a pointer P pointing on the same location where num is pointing. And then we set I to 0. And the for loop iterates as long as I is less than 5. So how many iterations do you think will this for loop have? The control variable is I. It is initially set to 0, and our condition here states that this for loop would proceed as long as the condition I less than 5 is true. So with this, your I would iterate from 0, 1, 2, 3, up to 4. 5 is not included because our comparison operator here is less than. So 5 is not included. It would only be until 4. So how many values are there? It is 5, okay? Because we start with 0. Now we start with value 0 for I because we would like to access the first element, and we know that the index of the first element is 0. Therefore, we set the variable I to 0. So this condition is true for 5 times. On the first iteration, this is true. And so we execute this loop body. And what is the value of asterisk P? Asterisk P means value stored at memory address P. The memory address P is 81. So it's like saying asterisk P is equal to asterisk 81. The value at 81 it is 6. So we display 6. That's why we have here on the first line output the value 6. And after the loop body, according to the execution flow of the for loop, we would execute these two statements belonging to expression 3. Okay, recall our previous discussion on the execution flow of for loop. This one is expression 3, and it consists of two statements, which are to increment I and to increment P. So these are the two updates you need to do before you proceed to the next iteration. So we increment I, your I now becomes 1. And P, what happens to P? P is pointing on this location, and so the value of P is 81. If you increment P, the value of P would become 82, right? So if it is equal to 82, then it is now pointing on the next memory location. So it's like we redirect the pointer P from initially pointing on num0. This time, it points now to num1, which is the one stored in memory address 82. So we cut this pointer and we make it to point to the next location, which is 82. And this time, the value of P is now 82. Num remains pointing on num0, and so the value of num is, for the whole duration of the program, it is 81 because we did not change it. What we change is only P, not num. So num stays pointing on the first location num0, while P, every iteration, take note, you increment it. Therefore, you are moving P from the first location, which is num0. On the next iteration, it points to num1. And then on the next iteration, it points to num2. And then on the next, it points to num3, and so on. So that's how we access the 1D array elements using this pointer P. Every iteration, we update P by incrementing it so that it would point to the next location, thereby accessing the next memory location or the next array element. So that's why on the second line, for the second iteration, the output is 1 because P is now pointing on 82 and the value stored in memory address 82 is 1. And then next iteration, you increment P. So from 82, it becomes 83, and therefore it's now pointing on num2. And when you display it, asterisk P, the value pointed by P, it is now 3. So the output here on the third line is 3. fourth iteration, you increment P, and therefore this becomes 84. So P is now pointing on 84. So P is not pointing here anymore. So let's erase this. So currently, on the fourth iteration, P is pointing at 84. And so when we display asterisk P, or the value stored at 84, it is now 8. And lastly, when we increment P from 84, it becomes 85. So this is now pointing on the last element located at location 85. And when we display asterisk P, the value stored at 85, it is 2. So that's the output on the last line. Now, why do you think we are using another pointer P in this program? Why not just use num, since as I mentioned earlier, num is also a single indirection pointer. Why do we need to declare another pointer like P, and instead of moving num, we move P? Why do you think? That is how we access the elements using another pointer P. It's because num is like a beginning marker that points to, or that reference where the array starts. So it is a beginning marker, and so you should not move it elsewhere. It is a beginning marker. It's like a landmark that is not intended to point anywhere except to the beginning of the array. If you're going to increment num instead of using another pointer P, you are moving num to the last part of the array. Okay, take note that when the for loop ends, the position of num, if you are going to increment it, would be pointing on the tail part of the array, or the location after the last element. And if you do that, you cannot anymore access the elements starting from the first element, because you move the beginning marker. So that's the reason why we have to use another pointer and keep num, the default pointer to the array, to position itself on the first element. For the fifth example, what we revise in the code is just to move the increment for P. Instead of putting it here, the P++, okay, that's what we have earlier in example 4. Instead of putting it there, we put this one together with the asterisk operator inside the printf. So this time, the expression in here has two operators, okay? Earlier, it's only one, asterisk P. So there is only one operator, asterisk, in the previous example code. But this time, we added this increment operator. So we remove the update for P, the incrementation for P, from the update section of the for loop, and we incorporate it in here in the expression. Now, since in this expression there are now two operators, asterisk, which is a pointer operator, and the other one is the increment. So since there are now two operators in this expression, the question is, which of these two are you going to perform first? Take note that these two operators are unary operators, meaning these operators takes only one operand. So when you perform incrementation, the operand is P. Asterisk is not included, unless there is a parenthesis that would override the default order of precedence for these operators. So every iteration, what happens here is that, take note, initially we make P to point to where num is pointing by this statement. That is our initialization for P. So we make P to point to where num is pointing, and every iteration we increment not asterisk P, but we increment P. So this expression is equivalent to saying asterisk and then open parenthesis P++ and then close parenthesis. Okay, so you increment P, not the value pointed by P. So there's a big difference to that expression. Saying asterisk P, this one you enclose in parentheses and then you put the incrementation here. This is not the same as asterisk parentheses P plus plus. Since we are using this expression, this one, which is equivalent to that, which is the expression we have here in the program. So how would this pointer behave now and what is the output? P is initially pointing on num0 with value 6 and every iteration you increment P. But before you increment P, you have to get the value first of P and display it because this is a printf. Okay? And take note that this is a post-incrementation, not a pre-incrementation. The fact that the incrementation operator appears as a suffix in the expression, it's on the right side. So you have to get first the value of P. After that, you increment P. Okay, so that's the action in here. So again, what is the action? First, get the value of asterisk P. Second, increment P. Again, increment P, not asterisk P. So every iteration, this is what we do when the printf is executed. So on the first iteration, P is pointing on 6. So action 1 is get the value of asterisk P. And of course, that is 6. And that's why in our output window, we have on the first line, the value 6. And then after that, we increment P. So P would now be pointing on the second location, which is the second element of the array, num1. And then we get the value of asterisk P, that is 1, so we display it here. After that, increment P, so this time P is pointing on the third element, and then we get the value asterisk P, that is 3. We display it on the screen. After that, we increment P, so P would now be pointing on the fourth element. Then we get that value and display on the screen. So we have 8 here. After that, we increment P. This is now pointing on the last element 2. Then we get the value and display it. So we have that value there, 2. And then increment P. So when the for loop ends, where is P pointing? It is pointing on the memory location right after the last element because you increment it. So on the last iteration, it accessed the last element, display that value, and then increment P, that's why it is pointing on the memory location after the last element. And that is the reason why we don't use num, as I have explained earlier. We use another pointer P to move around the array so that the default pointer num, which is the beginning marker of the array, will always be pointing on the first element so that whenever we want to access the element, we could always access it starting from the first element. And why can we do that? Because there is a beginning marker. If you move the beginning marker, you can no longer access the element starting from the first element because there is no more a marker that marks the door or the opening of the array structure. Now, what if instead of asterisk P++, we use this expression? We enclose in parentheses asterisk P. And then after that, we have the increment. Is there a difference in the behavior of the program and in the output? What we used previously is this one, right? And then second, what if we change it to this one? What do you think will happen? So say we change this one to this expression enclosing asterisk P in parentheses. What will happen is that what we increment is no longer P alone, but what we increment in here is the whole expression asterisk P. So again, for this expression, what we increment is just the P. Asterisk is not included. We increment P in here, but in here, we increment this value. In here, we increment P, in here, we increment this one, asterisk p. So that's a big difference. It's not the same. So in this case, if you use the second expression by putting this parenthesis enclosing this sub-expression, what will happen is that at the start of the for loop, upon initialization, you make p to point to the first element, num0, where num is pointing, okay, because you assign num to p. So you make p to point to that location when the for loop starts. And every iteration, you increment asterisk p, which is this one. This is asterisk p, or the value pointed by p. This is what you increment. And so, on the second iteration, this becomes 7. The third iteration, this becomes 8. On the fourth iteration, this becomes 9. On the fifth iteration, this becomes 10. So, the value asterisk p would proceed from 6, 7, 8, 9, 10. So, this will become the output of the program. When you change the expression to quantity asterisk p plus plus instead of just asterisk p plus plus, okay? So again, this is the output if what you have in here is this expression, parentheses asterisk p plus plus. If it's the original asterisk p plus plus without parentheses, you are incrementing p, and so the output would be this one. The action here would be to initially set p to point to the first element, num0, and then every iteration, you make p to point to the next element. So p is moving. From the first element, it is moving, going to the last element in the first case, okay, for this expression. But on the second case, when you use this one, p is not moving. P is fixed, pointing on the first element, and for the whole duration of the execution of the for loop, p is always pointing on num0. It is never moving, and what you increment is just this single value, which is initially 6, and when you increment it every iteration, that makes the value to go from 6 to 7, 8, 9, 10. Thus, you have this output. Okay, so this is for the first case. For the second case, it is this. At this point, we learned the two ways to access array elements. First, using the array name. This is how we access the array elements. The array name and then the array index. Second is by using another pointer like p, a single indirection pointer, and we make use of the expression asterisk p plus plus. Every iteration, you retrieve the value pointed by p, and then you increment p. Okay, so that's the second way. This time, we're going to discuss the third way to access array elements using the default pointer, which is the array name num and its index I. So this is exactly the same program we have earlier, and we simply change this part here. Instead of this and that, we use the expression asterisk num plus I. So what do we mean by this expression? Now, recall from our previous discussion that the array name, which in this case is num, okay, num is the array name. We discussed last time that the array name is by default a pointer to the first element, which is num0. So we have here a single indirection pointer with the name num pointing on the first element, num0. You don't have to explicitly declare this single indirection pointer. It is a default action of the computer that whenever you declare an array, that array name is automatically a pointer to the first element. So again, by this, num is equal to the memory address of num0. So num is a single indirection pointer. because its value is a memory address. And in this example, we're going to demonstrate how to use this default array pointer num to be able to access the array elements. Look at the for loop. In this expression, we have asterisk and then the quantity num plus I. So initially, num is equal to the memory address of num0. Say for example, this is address 81, and so this is address 82, 83, 84, and 85. So again, these are 81 to 85 are memory addresses, while these values here are the array elements. So on the first iteration, when you set the index I to 0, this would be asterisk num plus 0. Currently, num is equal to 81. Plus 0 of that is simply 81. And then, with this asterisk, you are trying to access the value stored at address 81, which is equal to 6. So, asterisk 81 or asterisk num plus 0 is equal to value 6. That's why the output here is 6. And for the second iteration, you increment I, so I now becomes 1. So this expression would become asterisk quantity num plus 1. So the num here is 81. So this is 81 plus 1. That is, the whole expression is equal to asterisk 82. Okay? Which means the value stored at memory address 82. The value stored at memory address 82 is 1. That's why the output here is 1. So take note that using this expression does not increment num. Num plus plus is not the same as saying num plus I. You simply add this value to num, but you never change the value of num. You don't say num gets num plus 1, which is the effect of this incrementation in here. So num plus plus or incrementing num is not the same as adding I to num. In here, we change num. In here, we did not change num. So since we did not change num, for the whole duration of, or for the whole execution of the for loop, num is always pointing on the first element. Num is not moving. Okay, it is fixed, pointing on the first element, num0. Okay, so the expression asterisk num plus I is the same as saying num I. In here, we simply put emphasis on the fact that num is a pointer. Okay, because we make use here of the pointer operator asterisk, which is to access the value pointed by the pointer. So again, these three expressions which we use in the first example for accessing array elements, and then the second one, and then the third, all of this have the same effect, or they have the same behavior, and of course the same effect, and of course produce the same output. So if we put labels here to these elements, this would be, in terms of this expression, the third expression, this would be, so num0 is equal to asterisk num plus 0, num1 is equal to asterisk num plus 1, num2 is equal to asterisk num plus 2, num3 is equal to asterisk num plus 3, and the last element, num4, is equal to asterisk num plus 4. And this is equal to 6, 1, 3, 8, and 2. Among the three ways of accessing array elements, It is the first one that is commonly used.